So now we take the output values G of S sub 6 and G of S sub 7. So that should be 7 there. And we compute an error. So the error function, okay, is defined as this. So you take y hat sub k. So for node 6, y hat, that is our output, G of S sub 6. So 4815. Okay. And y hat for 7 is this. So now the actual value of y, remember 6 is dislike the cheese, so target is 0, 7 is like cheese, so target is 1. So then 1 minus y hat and then y minus y hat, and you multiply these three numbers, then you get the error. So once you have the error, then we take the error and propagate it backwards from the output layer through the hidden layer back to the input layer, and we update all the weights and the biases. So this is how we will update the biases and the weights. So you take the old bias and the old weight, and then you take the error, right, the error that you have, multiplied by a learning rate. Okay, the learning rate is a value between 0 and 1, and very small learning rate would mean the update, the changes that take place to the weights will be very small, so it will slowly, it will take longer to achieve the final results. And if you have larger values of L, then the updates, the changes to weights would be large, and because of that there will be too much of oscillations. The weights will go up and down, so one may skip an optimum value because you're changing the weights way too much from one iteration to the next. So there are positives and negatives, so you have to typically you'll start with a small L value, like maybe somewhere like 0.01 or 0.02 or something like that. And there are some adaptive techniques that we can use where L changes. You change L depending upon how well the algorithm is doing. But let's start with example of say 0.5. So if L is 0.5, so these are the old weights. Okay, for node 6, okay, the old weights are minus 0.04 and the three weights coming into 6, and then minus 0.015 and the three weights coming into 7, right? So these are the old weights, and the error for 6 is minus 0.12, okay, and error for 7 is 0.124. And then you multiply the error by the L value and add it to the old weight, then you get the new weight. So now we have new weights for nodes 6 and 7. So now we have to we have completed updating the weights for the outer layer. So now we move backwards to the hidden layer. Okay, so now in hidden layer we have three nodes, right? Node 3, 4, and 5. So we have to first figure out what is the error attributable to each of the three nodes. So node 3 has errors coming in from 6 and 7. The error for 6 is minus 0.12, error for 7 is 0.124. So you have error here and an error here, and these two errors are propagated back to 3 based on these weights. So you multiply the error of 6 with the weight and error of 7 with the weight, and that sum becomes the error for node 3. And same here for 4 and 5. You multiply the error with the weights, and then you get the error for nodes 4 and 5. So let's take node 3, and we have the error node 6 and 7, the weights, multiply the weight with the error, okay, and add them up, and you get the error for node 3. And then you apply this error to the weights of node 3. So node 3 has a bias and two weights coming in, one from input layer node 1 and then input layer node 2. So these are the three weights. Then here is the error, multiply by the learning rate and add to the old weight, you get the new weight. And do the same for 4. So you have the two errors from node 6 and 7, multiply by the corresponding weights, and you get the total error attributable to node 4, and then you take that error, multiply by L, and you find the new weights. Repeat for node 5. So now you have completed the backward propagation of the error for the first observation. So now